Hey, welcome to Coffee Compiler Club. We're here today to talk about compilers and language runtimes and garbage collection and typing systems and nil or not or whatever. And we're being recorded live, and this goes up on YouTube generally within a couple hours afterwards. And I'm reserved the right to moderate, never had to do it. And that's the opening spiel. And then we have one new person. So David Lynn here, I guess. Would you introduce yourself and tell us what you are doing with compilers?
Okay, hello everyone. I'm very happy to be here. My name is Lin, and also you can call me David. I have some experience working on DC, the garbage collector. I have experience working on Android runtime and OpenJDK, and also I used to work in Intel, and there is a self-implemented Java virtual machine, and there it's running on the BIOS. So it's a micro runtime, and there is some requirement for the performance. And I used to write the assembly interpreter for that virtual machine. And it's a lot of coding work, and especially it's hard for debugging, but the performance got maybe about 30% improvement. And recently, I'm working on a little bit about the compiler, but I'm in the Web3 blockchain field. I'm trying to do some research to see whether I can make AOT ahead of time compilation for the smart contract. But I just start the work and have several problems. The first one is that the smart contract. The execution speed of the smart contract is actually determine how fast can the block to be graded. Actually, for a block, we can treat it as a bunch of smart contract execution result. So especially when you have one single smart contract, the performance may not be so much important. But if you have a bunch of them running one by one, and you need to collect the result and record them on the blockchain, which means you generate a block. So that means you need to do some performance work. And I have know that there are some work related to JIT, just-in-time compiler. But the problem is that the compilation time, they actually take effect to the runtime performance of the smart contract. And especially every smart contract, if they are not too large or they are not too heavy workload, the JIT compiler may take much more effect. So I'm thinking of using maybe AOT, but the AOT, they have the problem that for every smart contract, the developer don't care about the architecture or the platform they are going to run. And the provider of the so service provider who help to create the block on the blockchain, they may use different architectures. They may use x86 or ARM. So it's hard for the smart contract to compile to different binary from the developer point of view. So I may need to to think of it, to know how to compiling the front-end language such as Solidity to the binary such as assembly language.
Okay.
Yeah.
Yeah. So
that's all.
I'm thinking that the obvious thing that you would do here is if you executed a smart contract once on a blockchain, you're going to execute the same contract a lot of times as the blockchains get shuffled around until they get stable and then they keep getting executed over time. Why would you just not JIT them and
yeah,
hang on to that for the process, which is doing the blockchain for the next time it gets run on the same machine?
I know. So actually, the scenario is like this. When they creating the blockchain, when they creating a block and submit it to the blockchain, there is a verification step. which means, for example, there are several services called node who actually run the smart contract and create a block and then submit the block to the blockchain. And another node service do the same thing to do the verification, which means they rerun those smart contracts and check whether the result is correct, and they make the consensus, and then they take the vote for the block to make the judgment whether it is correct to be on chain. So the problem is that the smart contract was not running once by once or repeatedly on one machine or one set. It's actually distributed, running repeatedly on different platform or different node. So the node can have different platform. So it's hard, for maybe one solution is that the smart contract can be compiled to several binaries and submit to the blockchain together, but it's hard to control the size. So here's the problem. Yeah.
Well, and you have to verify that the code that you're receiving, actually executes the semantics of the contract. Are the contracts you're looking at typically, how long do they run?
Well, every contract may not take too much time. There may be a 1 or 2 second workload. There may be, just some contract to transfer some money or some token from one set to another, one person to another.
That's going to take a second to run?
Nearly. If there is too much work, it may take a second, because all the virtual machine for the smart contract is actually an interpreter. So
sort of a tier 1 JIT will easily be done well under a second and give you
a contract, not a fast contract.
Yeah.
Okay. So a tier 1 JIT, do you mean that there is no optimization, no profiling, or not too much profiling work?
You profile in an interpreter typically to decide that it's worth JITting. So you have some trigger. So it counts loop back edges and it counts function calls, or some trigger says it's time to JIT this thing. Yeah, and then you don't do heavy optimizations. So this can go what I guess I would call a tier 0 or a template JIT. Just slap down the interpreter instructions without the interpreter dispatch loop one after another. Skipping the interpreter dispatch loop is probably a 2x speed up over a good interpreter. If you then first go to an IR and then come back out and you do nothing except spit machine code for the IR, which means you do register allocation and a tiny bit of instruction selection, you're probably another 2x to 3x over what had come before. So like a tier 1 JIT ought to give you 5x to 8x over interpreter, or something like that. And a tier 0 JIT gives you 2x over interpreter.
Okay. I think I can try it. Also, I have another idea. I'm not sure whether there is implemented before or designed or think before. The idea is that there are actually, for one block there is a bunch of smart contracts, which means you start up the virtual machine, you run the one contract, and then you wrap down, you do you repeat for another one. So I'm thinking of, is that possible that we do the profiling based on all the smart contract in the one block, and then we dump all the half-git code and do the compilation, and then for those common code we can speed up by using compiler technology.
Yeah. You have a firewall between the contracts from a conceptual point of view, but from the implementation of the blockchain, there's no firewall between them. You just run them all together. As long as you keep the semantics as if they're running independently, the code can all be shared, including all the JITted code. If somebody's rerunning the same contract but with different numbers every time, if stock X got above stock Y, transfer money Z from A to B, but that same contract runs 1,000 times with different versions of stocks and values and prices, JIT it once, everyone uses the same code, they just function call with the right set of arguments.
Okay, thanks. I think
Yeah.
I have a lot of work to do after work. Yeah.
Yeah, no problem. Are we done with smart contracts for a little bit? Darrick wanted to say something. And
Yeah, just have to unmute here. Yeah, so I've been making progress as usual, and finally kind of got out of my iterated bug squashing that was almost killing me for a few months there, and sort of moving forward. So I'm at instruction selection and just trying to work through some details there, and then register allocation is, so I basically instruction selection, I think I've got.
Is this on the PE or the risk side?
Both, yeah.
Both,
So I had the instruction selection for the risk several months ago, but then, you know, I made a lot of changes, so I had to go in and update that. And I thought it might be interesting to show a little bit of what I was doing. So one of the things that I decided to do in the last couple of weeks is generate the call site convention stuff. So like putting stuff into the right registers and whatnot into the graph. So basically do that kind of as something like an ideal pass before.
C2 does that.
Yeah. So I ran into a bit of a problem with that I could do basically some machine specific ideal pass that was just like an ideal pass. And so I added those. And then when I was generating registers and whatnot, I realized that where they go in the graph is really important. And I had to change my approach. So what I ended up doing is scheduling the code and then walking through the scheduled nodes one by one, and inserting items at like adjacent to the scheduled code. And also, as I was walking through that scheduled code, I could kind of keep track of basically almost new variables. So I could, for instance,
calling convention.
Well, yeah. So for instance, the return address that a function gets, like I don't have anything in the graph about the return address, which is kind of an argument into the function.
Yeah, that's how C2 treats it. There's an
Yeah,
RPC edge in and an RPC edge out. Yeah.
Yeah.
Well, the RPC edge at the end goes to the return, which is basically a multi-way jump to the back to where you came from. Yeah.
Yeah. So I didn't have that as an argument modeled, and it didn't actually occur to me until I just said it just now to treat it that way. What I did instead is, as I'm walking through, and so I basically decided to do a walk through all of the functions and blocks in reverse post order, traversal order.
Yeah.
Insert nodes as needed, and then I can sort of put in that I'm using a register here, or using the like
missing some about where you're putting nodes in for you're using a register or not.
Yeah, and I basically was trying to wire it back up into the graph so that I had what graph context I needed as I'm doing this walk in order, and then I can as I'm building things, I can wire them up so that I can then do another ideal pass later, and it won't kill everything because things aren't wired up properly. Does that make sense?
It kind of does, but I'm missing the whys. But hang on.
Yeah.
When I do this in C2, at some point I declare I'm done with the standard ideal stuff. I do instruction selection, which just replaces one whole graph with another where minor ops are folded up into Intel, load address, store, shift, multiply, add, blah, blah, blah. Call instructions are swapped for machine call instructions, which are basically extend call instruction as an object-oriented thing.
Yeah.
But they pick up the calling convention. And so every input edge and every output edge gets a bit mask for allowed registers. So that covers your calling conventions and your weird Intel ops for multiply and divide and stuff like that.
Mhm.
And I end up, so this is a graph for graph swap. Basically, I walk one graph and write a new one, throw the old one away when I'm done. Now I have a new graph. It's just one pass walk. Now I have a new graph that has registers counted for every input and every output edge. And now officially I go into the register allocator. Well, I guess I could do instruction scheduling next.
Yeah.
And then I go into the register allocator.
Yeah. Okay. So yeah, I guess this approach added an sort of an extra or like a slightly earlier than I expected scheduling operation. And then I'm generating a bunch of nodes into it. So
I guess I'm saying I didn't do that. I made one ideal pass to swap ideal nodes for machine versions. Now I do a scheduling pass that adds no nodes. It just pins things down to basic blocks.
Yeah, so that's what my scheduling pass is identical to the one that you published. So I'm doing that, and then after that, I'm sort of walking through and adding into the schedule. So I think that's where it's.
Once I've got myself in a scheduled with machine nodes, I now declare myself in the register allocator. And the register allocator inserts nodes because he inserts spills, but no one in between those two do.
Yeah. And do you wire the spills up, or they just sit positionally in this?
They're wired in the graph.
They are wired in.
So at any point, I can do a standard graph walk. In particular, the pretty printers I use for debugging all do standard graph walks.
Mm-hmm.
So the pretty printers all continue to work.
Yeah. So when you, so does a spill then look just like a normal memory write? Yeah.
It's declared as it's a machine specific version. It targets any register and any stack slot for both input and output. Otherwise, it looks like a normal machine node, ideal node that's a move thrown in the graph.
Yeah. So just like a normal memory write, you would have would you have the edge that sort of connects that memory write back to a previous version of the memory?
No. So be careful here. Stack slots are not memory.
Mm-hmm.
Stack slots are a register. You have an infinite set of them.
Uh-huh.
So there's no memory edge involved. It's a reg-to-reg move. One of the register targets is a stack slot. There's no memory edge on them. They don't alias with anybody. They have no ordering with anybody.
Okay.
Maybe that simplifies what you're trying to do a lot.
Maybe that, yeah, I think that might. Well, that's the part that I haven't kind of worked out yet. I had stack stuff in my previous representation, but that was just like an standard IR type representation. Right.
So when it comes time to start doing stack things, treat the stack as an infinite pile of virtual registers, not as memory at all.
Yeah. Okay. So then it's basically just so if I create a move of data into a stack slot, I just basically do a write into that node that represents memory that represents data that's been written off into the stack.
Yeah. So
I do a read from the same node later, and that just pulls that memory out.
Yeah, but change your lingo. You don't do a write into it. You do a move.
A move, yeah.
Right. It's really a register move.
Yeah.
It happens to, load and store out of the stack. Don't think of it that way. It's a reg move, because that's all about how your register allocator is going to color. It goes into the you know, graph coloring simplification algorithms. It goes into anyone else's aliasing hacks. You can bypass these loads and stores with other memory rights that are actual language specific rights to do whatever. These are all completely independent.
Okay.
They're not memory anymore.
Yeah. Okay. Okay, that makes sense. I can show if it's interesting. I don't need to. How this kind of looks in the graph in a small graph that I've been using as an example here.
I handed you the display.
Okay. All right. I'll just
Yes, in register allocation, the sea of nodes, Theodore. There's some conversation there. That one has nothing to do with sea of nodes. Spilling as a red move to an infinite register set is register allocation. It's not really sea of nodes.
Okay.
This is like anybody's register allocator can do this hack. So the other fun effect out of that is that you graph color your stack slots. You never run out, so there's no spilling. It always colors, but you get a much tighter stack frame than I've had in the past until I started doing this hack. So the stack frames come up really small too. It's one of the nice side effects. Are you going to display something, Darrick?
Yeah, I just had to bring it up here. So, let's see. I just make this a bit smaller.
Yeah, I have to.
So is that legible? So here
font size a little more.
Okay. Yeah, so it's a balance between seeing more of the graph and seeing what's in the graph. Let me make it small first, and we'll sort of see the overall view. Okay. So what I've got here is this top bit is one function. And then here's a program that stores something in memory, calls that function again, and then adds the result up. The function adds the argument, stores in memory. So this is pre any machine stuff. And so if we look a bit closer at it, the function is just called Z store. So there's the function call node, function return node, and the projections. And so like basically one return gets used as an argument to the next call, and then the returns get folded up like this.
Yeah. Okay. Animal. Yeah.
After I run the machine pass on it, it ends up looking like this. So this is the same thing. So let me zoom out again.
You have a lot more nodes now.
I've got a lot more nodes because it's putting things into specific registers for the calling convention.
Oh, and you put those as on the graph edges.
Yeah. So
yeah, I didn't do that.
So I hear like register 8, register 9. Those are the two caller save registers.
Right.
There. This is my return address.
Yeah.
So it gets. I have stack node here, which maybe this is wrong, but and then I've got a stack pointer node. So basically part of the input to the function is the value in the stack at 0 is the return address's stack pointer. So I write this stack value into the stack pointer. Into the,
You got something backwards here. Where's your return address come on your, is this for PE code or is this a RISC code?
This is PE code.
Okay.
This is RISC code, sorry.
Okay, and the return address for the RISC is put in a register or on the stack?
The return address is ends up in GR1.
Okay. Very common.
And then when I make the call, the stack pointer location for the stack frame is put into the stack at the first entry.
You're pushing the prior stack pointer basically into the frame.
Yeah.
And then presumably you bump the current frame as needed for having your spills if you're going to have any. And then on exit, you're going to pop the prior
That's right. Yeah. So before it, this
And why
function
are you
leaves,
doing
it
that
pops.
instead of just adding and subtracting? Like the usual story is I add for my current frame, and right before I exit, I subtract off the stack pointer.
That's a better idea.
Okay, fine.
Yeah. Okay. So, yeah. So I mean, so the representation I have here is that this is the constant of the function location. I put it into gr1.
Yeah.
The call is basically a swap, and it swaps gr1 and gr0. Gr0 is the program counter.
You don't have technically a call instruction. You just load
That's
the
right.
immediate address in a register and.
Yeah.
Okay, fine.
And I put this value into gr8 and
something else into gr9.
Yeah.
Do your thing. Okay, yeah.
Yeah. Oh, gr9 is down here.
Okay. Yeah.
And yeah. So that's basically how this works. And then the projections are named for the register where the data would go into.
Right. Yeah.
There was another pass that folded up identical returns into the same projection, so I could save some registers. Yeah, so that's kind of where I'm at. It seems like this is a workable representation.
Like I said, I didn't put the instructions, every possible register in a node just to label it as where it came from. I did a edge to edge thing. Then if I had spills, you had that effect. You know, if you passed a value in a register and you promptly wanted to pass it along to a new call in a different register, you had to have a spill and just moved it from gr8 to gr9 or whatever it's going to be.
Yeah. Yeah. Okay. Yeah, I think this will work. I've got a similar nodes that are PE registers they're just numbered as well. And yeah, and then the idea is that I'm going to run the register allocator once for the risk registers, and then just run it again for the PE registers, and it should be fine.
Yeah, sounds
You're
good.
ready.
Yeah, there's no crossing per se between them that makes sense.
Crossing.
Yeah.
Yeah, anything that crosses between them is very explicit.
Yeah.
Yeah, and I've for all the sample code that I have the full instruction selection. But for the instruction selection, I'm just basically creating a list of nodes in the old IR and not trying to put it in the graph, because one of the things that I don't really know how to deal with is some instructions aren't really one instruction. They're a sequence that seems to have to be run sequentially. So like you have to do something that sets a flag, and then you have to use the flag immediately. So I don't know if I create like hybrid graph nodes that are that like whole sequence of instructions.
Okay, C2 treats them as a single machine node. It has only slightly more complicated register allocation issues. But the graph doesn't tell it apart. So like if I have a locking idiom where I need to do a CAS and a jump on a fail to a slow path, and it looks like a branch off from the IR's point of view, but it uses several registers and maybe an internal, and it kills flags.
Yeah.
So I declare myself to kill another temp that has to be described in the machine instruction. So the register allocator allocates you a temp to be crushed. And he has two inputs, and he has a result on the swap as one output, and he has a flags as another output, except that would get consumed. Your case, I get consumed by jump immediately. So then he's just an if instruction that consumes a bunch of registers, kills flags, and jumps to two different targets. But internally, it was 3 or 4 ops, of which one was very special. So there's a bunch of those kind of idioms where something weird was going on. You wanted to do a mul div folded op on some hardware. It was 2, and some it was 1.
Right.
So internally it had a fat encoding. When you spit out the instruction, it had a fat encoding. From the compiler's point of view, it was a black box. It didn't fall apart. It didn't break up.
Okay, so that's a good way to represent it.
Okay. Well, it worked.
Yeah.
If you did, we did a bunch of things. Like like the register allocator, the read barrier has a couple small parts, but it's extremely commonly executed. So there's some payoff to break it up, even though it screws with your graph semantics. Having, not your case, but in Azul's read barrier for their GC. The write barrier was simple enough that we didn't bother to break it up. So on an x86 write barrier for the longest time, I don't know what they're doing now. The longest time it was, you know, burn a register, shift write by 9, add to a base, store 0. Done in like 2 ops, and no one broke the 2 ops apart.
Mm-hmm.
It's just a black box. Fine.
Yeah. Okay. Well, yeah, I'll try that. So I think, so my I've come up with a plan for how I can transition myself from my old representation to the new one. I think the pass that goes from the graph to S expressions and then into the old IR is basically just sequentially walking each node of the graph and producing a nice looking representation that is missing a bunch of information, but is easier to read.
Yeah, right.
And but I realized that there's no real need to walk that structure. I can just walk the scheduled graph and use my pattern matchers on demand, basically generate that view per node, match against those, and still be looking at an actual graph node in reality. So I'm thinking that
potato chips. You can't just eat just one.
Exactly.
Now, if this part in the new sea of nodes IR, oh, this next part's really easy. Oh, the next part's really easy. Yes.
Yeah, exactly. So
join me.
It's good. I mean, I basically, that's the goal, to eventually have everything, you know, in that mode. But, you know, I had some kind of nice functionality in my previous thing as well. So when I did the select instructions, the representation it generated was just directly executable. So I could just eval that and it would produce my bytecode.
Okay.
So, and I basically just had a bunch of functions that had like arguments that, so I basically was just generate, like it became a kind of macro that generated my final bytecode, and then I'd run it and out would pop like a bunch of bytes. So that was kind of handy, and that was all generated by data structures that represent our instruction set and all this.
Because you're running Lisp.
Yeah.
And all code is data, and all data is code.
Exactly.
Okay.
But they don't have a graph node for some reason.
Yeah.
Need a new list.
There's a semantic somewhere in there that you can go deal with, but you have some level mapping to go through, I think. I don't know. I had a lot of questions on those sorts in the land of C2, where we kept wanting to pre-compute, and eventually that turned into make a bunch of IR, like reflection was make a bunch of IR and then hand it off to the bytecodes and then let the VM run it. And then eventually the compiler saw it as executable bytecodes.
Like you go through the entire compilation pipeline.
It went through the whole fucking pipeline. Yeah. We tried a couple other things, and there's definitely some places in C2 where I inlining intrinsics, and I just have a toolbox approach of being able to stamp out IR in large volumes, where I can say grab some of this and grab some of that and stick them together. And there's no bytecode for this. It's somebody's running the system.array copy. It's not, but that was done a different way. But a bunch of these intrinsics, you know, they would stack up 10, 20, 30, 40 nodes in the IR, and I had a way to stitch them all together. It was reasonably sane to read. I think big ones were the longest time we could use the Intel sine cosine ops directly, but to head into the edge cases, you had to test for all these bit over and underflows and do optional special expansions where you're bit twiddling and shift right until kind of crap. And so there were loops and there were, I don't know, and that was the expansion. Like it'd be a pain in the butt to write that as Java or as Java bytecodes. So it only ever came out as IR and only on an x86. But it came out as raw IR, but it looked like plain old IR. And then the optimizer went to town on it. The only thing weird was you had a special sign op in the virtual ideal world that turned into an Intel sign op that did the, the hardware encoding.
Why was it only on x86?
Because only x86 had a sign instruction in hardware.
Oh, okay, I see.
Yeah, back in that era, the complaint from the C guys was, you suck because your sine and cosine are slow. Like, you suck because you don't do this thing. Well, of course, sine and cosine were using the Intel op, which had horrific edge case condition issues. Like, it was not well structured if you got near the edge of the world. And Java wanted to be, bit for bit perfect on IEEE 754, which means you had to handle all the edge cases perfectly. So all these benchmarks were giving Java a public bad name for screwing around doing, I can do sines a million times faster than Java. It's like, oh, come on. Like, no one cares to do sines a million times faster. What the hell? So I had to go do it anyhow. And so, I had to do that. There's a bunch of those where I had to go do because.
So to be fair, Java definitely did not do IEEE 754 by the book, but the sines and cosines were one that it got.
There were some specific things that we threw out of the spec. Like, we didn't do all the nans. We picked one nan as the.
Yeah, there were a bunch of discrepancies, but yeah, the worst one was doing anything on the Sun chip was like, you might as well just take a vacation and come back. Like log 10.
It was like IEEE 754.
Yeah, but a log 10 operation on a Spark took 2.5 weeks. Like,
I did not make Spark
burned
hardware.
more power than the state of Tennessee.
I did not make Spark hardware. I went through SoftLib.
Because we had we used the log 10 on a cache eviction algorithm to do to basically do what we thought was a cheap histogram. Obviously not very cheap. And it,
what are you doing logs in a histogram for?
And we had a customer deploying it on Sun, and we well, it was a long story. Like, we were trying to combine multiple factors and basically do them logarithmically, but turned out it was burning like 90% of the time just in log 10 operation.
Yeah.
On a couple $1 million worth of hardware.
Log 2 by doing the higher bit algorithm in one clock.
Yeah, log 2 is probably what we switched it to.
Yeah. I've done plenty of histograms of logarithmic, but always log 2, not log 10.
Right. Well, log 10 is just the log function, if I remember correctly. So, I wasn't thinking log 2 versus log 10. I was just thinking logarithmic.
You were doing log, but I'm doing like higher order bit. Don't do log. That's like fucking floating point math. That's slowing everybody back in that era. Dude, never mind.
That's why you set the standard library when they don't specify a base to use E.
Yes.
I was working on a logarithmic histogram, power of 2 histogram a couple weeks ago, just trying to see how little memory I could fit it in. And like, including Java header, I got a 64 byte histogram that can handle all long values. Fun stuff.
In 64 bytes?
In 64 bytes. Yeah.
Okay.
I made incrementing the bucket counter was probabilistic based on the current count. So like,
oh yeah, right.
Yeah. And then don't need an array. I just needed I think six longs. And so it was like whatever it was, 30 something, six. I needed 64 6-bit counters or something like that. Yeah. And like the whole thing plus object header came in like exactly 64 bytes, which meant it had to be right.
Yeah, okay. I have done hacks like that for that kind of reason as well. There was something I was doing where I needed performance profilers or approximate counts in a logarithmic scale. Yeah.
It's a good idea. So you increment how does that work? How does that
I think like forgetting the trying to make it as compact as possible. You have 64 buckets that are each a byte, right? And the value that you store in each of them is going to be a power of 2 number, right? So each time, so then like you can go from 1 to 2 to 4, right? But you don't get any of the intermediates. But then how do you know when it's time to increment it? Well, if the current value in the bucket is 4, then you say that I want to try to increment it 4 times before I go to 8. So the probability should be 1/4 of the time. So thread local random next int of current value decides whether or not you shift by 1.
Right. But how many randoms do you have to do to? So you end up doing a lot of randoms.
Yeah.
One random per increment, per attempted increment.
Well, no, yeah, every time you try to add something into the histogram, you do a random, and if that random ends up being 0, right? So random of current count. If it's 0, then it's like, okay, now it's time
the random against
double. So
yeah,
of the current bucket, right? So when you've actually in a given bucket you've managed to collect 16,000 samples, you're going to need another 16,000 times before it's likely that you'll bump it up to 32, which is kind of the right value.
That's roughly the same way I did the infinite counters in 8 bits, was you do the random based on the top bit that you have.
Oh, I mean,
to see if you add 1
TSC register.
So basically, instead of being 2 to the 8th, it becomes 2 to the.
Does it become
I can't
log?
remember. Each one goes up as a logarithm.
Right.
So So you get big numbers.
Or you can track big numbers without big space.
Right. The challenge is that for some reason, most processors don't have a very, very cheap non-secure random. And it's just crazy. Like that's one of the ops that should be built in,
Yes. Free read.
Like a random register, basically.
Circuit. On Azul, I could grab the count register in 1 clock and just take the low bits.
Right.
That's my random.
That's the type of thing you do on x86.
And x86, I went to TSC at some point, and then TSC had this history of being either cheap or expensive according to the phase of the moon.
Right.
Low bits of the tick counter are relatively cheap random.
That's what we're saying. Low bits of the tick counter, TSC. If you're a hypervise of a certain generation, the hypervisor would intercept TSC register to try to make it monotonically counting. Which
that was like 15
times.
years. That was like 15 years ago, though.
They don't do that anymore then?
I don't think so.
I thought they had stopped. I wasn't sure when.
Now the hardware does it.
Okay. Yes, like it should.
But it's still like it's not in like the Java language specification doesn't say anything about it being monotonically increasing. So it's like nanoTime. Like I'll just pretend that it is, and most of the time it is.
Right. Yes.
But it doesn't have to be like any clock. It doesn't have to be monotonically increasing. Like if you're just using it for random.
Yeah, just using it for random.
Oh yes, for random, yeah, But for random, thread local random is so insanely fast. It's definitely faster than getting the time.
Yeah, but thread local random isn't available at an assembly level. So.
But it should be.
That one.
Actually, I had a TSC related question too, since we happened to hit on that, or more specifically, a time question in Java. Is there like a full fence around currentTimeMillis or nanoTime? Like, what are the reordering constraints? Because I can't find them anywhere. So I mentioned a couple of weeks ago.
Right. I'll tell you what the rule is.
Clock.
Yeah, there's a rule, but there's no rule. But many large Java web server things, J2EE apps would crash if currentTimeMillis didn't have a happens before relationship between different tick values of it. So that one had to be done like brutally under the hood. There's a thing there that basically forces a happens before relationship. There's no cheating allowed.
Right, and it's
there's a
but that's still like, but that it happens before with respect to what, right? Because it's you only get to do read operations
to any other thread who reads a tick that's off by 1 from you.
Okay, so each time I read the clock, it's also as if I've written the clock, so that when someone's so there is a full fence then.
There's some kind of full fence there. Yes, the implementation of that has varied across architectures. On Intel, as of 15 years ago, it was read the Linux fastest get time of day, which reads some kernel memory. that's a 64 words or 64 bytes, not more than several words, 4 or 5 words. Read it again, confirm that you got an identical read twice in a row. So if you don't get identical read, you go back and read again. So you basically read a wad of memory atomically by trying until you get an identical read twice in a row. That's sufficient to force ordering on all Intel platforms up to that era. I think maybe you're correct. You also then do a write, and then that's for Intel. That's enough to give you ordering. Azul had the tick counter, and we knew it, and it was cross cluster wide, and so shift scale add on the tick would give you currentTimeMillis, and we threw down the necessary fence to make that happen when we discovered this issue.
So that would prevent. So I mentioned it a couple of weeks ago, right? Writing a super cheap to query clock, which basically background thread once per couple of millis writes into a volatile, and then everybody reads from it. And I started thinking, well, but there's nothing, like if I was timing 2 things with those 2 volatile reads, nothing's preventing the second one from floating up and joining the first, or up to, but not intersecting with the first one, right? So that you don't end up timing anything. Like, crap, do I need a fence on my clock read?
You make the OS take a read-only page and update it once a millisecond with the currentTimeMillis. Everyone who reads it will invalidate their cache at the time they read it, and it's declared a volatile read, and they'll get their order. But
okay, but if the same thread reads it, does some stuff, and then reads it again, can that second read float up? And be reordered with the stuff.
You make the read be a volatile read, and then it will not float because it's declared volatile.
But volatile reads can float up; they just can't float past another volatile.
That's
right. So if I have volatile read, the bottom one can float up and get up to the point that hits that, right? So if I'm trying to measure something, right,
yes,
it can't, if I'm trying to measure what's in between, I can get 0 out.
No. If you want to go in between, you got to do nanoTime. You're doing currentTimeMillis. He could float 2 reads of currentTimeMillis adjacent to each other. Yes.
Okay. So what about nanoTime prevents it from floating?
Oh, the nothing except that the intrinsification of nanoTime puts a hard fence in on purpose just for this reason.
Okay.
But that's nothing in the spec. So you know, and already the spec's loosey goosey here. So you know the hardware can roll nanoTime backwards on you anyhow. So you know what the hell are you gonna do about it? So you
so that's I got with my clock a couple times. I did the work. I put the fence in. I profiled it. I'm like, yeah, I should have the fence. I'm like, no, I can't look. It doesn't need to be there. Like the nanoTime doesn't give you any such guarantee. But if it doesn't give you the guarantee, you can't actually time anything.
It's true.
I keep going back and forth because it infinitely increases the cost of my free clock read. And by infinite, I mean it adds a half a nano.
Okay. I'm just saying, none of this is in the spec. So, and I did nanoTime umpteen years ago. So who knows who's screwed with it since then. But nanoTime was clearly intended to do, so we put a fence in. A compiler fence. Whether the hardware did a fence or not.
Yeah, read TSC, I think, has a hardware fence.
Yes, that one has a baked-in hardware fence.
Compiler fence.
But you had to have a compiler fence, too.
Right.
Okay. Yeah. And the militime did not have a compiler fence put in, but we did put in the volatile read effect. But he wouldn't fold 2 millis together back in that era. I don't know if he does now, but he would let you say it's a volatile read of an intrinsified wad. Oh, you have another volatile read of an intrinsified wad. You have some other unrelated things going on. They can bypass volatile reads, and the 2 volatile reads go back to back. Yes, that could happen with militime.
Awesome.
But the cross thread one was the bitch. That's why the volatile went in there in the first read.
Right, and then clock skew anyway, and it doesn't matter.
We had plenty of people bitch and moan and die because of that kind of effect.
Did you do the same thing at Azul?
Yeah, no, it was at Azul that we did it. And then I was talking to Steve Goldman at Sun while he was doing Itanium port. We were racing to find the next data race because Itanium was loosey-goosey architecture over x86 or Spark. Azul's loosey-goosey over x86 or Spark. So we had all these races on the runtime we were both discovering. So we were going back and forth, and we swapped data race bugs with each other once a week at least for 6 months or more. Amongst them were this kind of games where militime, because I had this completely unrelated implementation of, milli times before the TSC was available in x86. I had a good TSC at Azul. So, it went on, and then TSC showed up, and suddenly it went on the other way with, the Sun folks come back to me. What happened here? Well, okay, blah, 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 blah. We swapped this race and that race and whatever. Back and forth, at least 6 months, maybe 2 years. It was a long time, and a lot of races got found that were hidden by x86 or Spark, but definitely in the core. Fine. It's fun stuff. And to this day, I know where so many bodies are buried in the core runtime that if you ask me to go break Java security, I don't know. Maybe not. Maybe they can fix it. But I had a bug that I had filed with Sun.
What Java security?
Exactly. I had a bug I filed with Sun.
No, they took it out. Like,
I can break your security, and here's the test case. And I left Sun. 10 years later, I got a call. Hey, does this bug still work? I pulled up the bug from their bug database and the test case, and I ran the test case, and it broke security. And I said, the test case as it stands in your thing breaks your security right now. Why did you call me on the phone? Fine.
Then you ask for your bug bounty.
I gave them a fix at the time I put the bug into the bug database. And then they chose to implement a different fix, which, to my untrained eye, didn't look like a fix. Fine.
I opened up a JDK bug a couple of weeks ago. Like, I found a memory leak in a completable future, and like pointed it all out down to the line, and they got back like, you just need to run system GC. even if that were the answer, that's not an answer, and that wouldn't also fix the case I showed them.
Is that what they call first tier support?
Yeah, wow. I think so.
Wow.
They're like, well, I looked it up on Stack Overflow. It says to call system GC.
I didn't know how to reply other than like, no, like, try the example I gave you. Like, that's not gonna help.
Wow. And you're paying for this? That's the support you're getting?
No,
Okay.
This was just like, I worked around it, but I'm like, I should be a good citizen and open a bug.
Okay.
Regarding leaking things, does anybody know what's the reasonable upper limit for files .delete on exit? Because that's also kind of leaky, and I'm wondering what's the maximum amount of files you would register for deletion.
What's your heap size?
I would thought there would be file handle counts, but maybe they're not. Maybe it's done by strings. That would be heap size, yeah. Is it not open files? It's just a named file to delete on exit.
Yeah, there shouldn't be a file handle.
So if you put a few million and it takes a few hours to delete on exit because the disk is grinding away, and somebody gets frustrated and hits Control-C again, did it matter? Why are you here?
That's actually a good point.
All the things that say, do this on exit, I expect exits to, I'm exiting harshly, not politely, because something's fucked up. So if you have a do this on exit, and it's anything faster or slower than human reflexes, my second Control-C came flying in already, and you didn't.
But your delete on exit files should be in the temp directory. So once you restart, you'll be fine. Once you restart your machine, you'll be fine.
Yes, yes. Restart your machine. Thank you. It's like Windows. Reboot it once a day where you need to or not.
And reinstall once a month?
Yes. And very frustrating because Emacs and Windows don't talk politely, so I lose my Emacs setup every time. Not all of it, but enough of it to be pissed at Windows for. There was a time when you could say, tell Windows you're on a metered internet connection, he can't download without permission, and that would stop him from doing updates. And somehow that has gone away.
Yeah, because they figured out that people were using that to avoid
that fucking update. Yes, thank you. In all my entire life of using Windows for 25, 30 years, I've had one virus, but I've had millions of reboots that were not necessary. So the cure is worse than the disease.
I imagine you don't download a whole lot of software. That's the pattern I've noticed. Like I never get viruses, and like all my family members do, but I don't, try random crap off the internet. Like,
Okay.
once I have my
Yes.
IDE, I'm good.
Maybe
If a
that's the
pop-up
answer.
comes up and tells you to do something, do you do it?
Yeah, right. Hi, I'm a Nigerian princess. I have $1 million for you. Just press this button.
Well,
Oh,
the
that
key
I
is,
How do
do.
you
the
get by
key is
without
to
the
only
Bonzi
trust
buddy assist?
only trust downloads of executables from Russian porn sites, and then you're good.
Exactly. I was going to say, not Russian porn. My son did it at grandpa's house, hit a Russian gun
Russian porn?
No, Russian gun website when he was like 12. That,
I don't know. I run make files I got from GitHub.
We're talking about nerd risk here. Random makes from GitHub. Yes, I do too. It happens. It's true.
You never know when someone's random make file is going to change you to a Dvorak keyboard.
Change your what? I lost you, Aaron.
You said Dvorak keyboard. That's a
Dvorak keyboard.
There was a project where someone who was trolling their users had, when you ran the install, switch your keyboard from QWERTY to Dvorak.
I missed that. Thank heavens. Yeah, that'd have been ugly. Of course, it's Windows.
They got banned from NPM for that.
Yeah. Okay. Sure.
Wait, so you can get banned from NPM?
There's an amazing pile of crap on NPM. The bar has to be really low. To squeeze under that bar, you have to do limbo dancer galore. I don't understand.
Yeah, I still haven't managed to fix all of my JavaScript projects after they took Boolean out of NPM. I don't know if you remember that one, but someone had like written a Boolean.
Oh, it's not even left pad, it's Boolean.
Yeah, it was literally like a Boolean project. They took it. They got mad at NPM one day and took it and went home. And like half the internet.
They should have just like only taken true. I'll leave you with false.
Or do what people used to do in small talk and switch true and false.
Yeah, right. My project, I'm gonna fuck you. I'm gonna fuck it with it how I want. What are you using my project for? Okay, fine.
But to be
The moment that I
honest,
had that was like that was trying to build Docker files that have the minimum possible amount of runtime there. And every once in a while you have those moments where it's like true, not found. And I was like, who's calling Unix true and why in this build?
but to be honest, we had a project in the past where the project lead created a fuzzy Boolean, basically a triple state bang, true, false, and unknown. Like
Java has that.
No,
Big B Boolean.
Exactly,
I use the third result all the time. No, like it's perfect.
Right. Oh, geez.
But he wanted it to be null safe, right? So he created a class for that.
What happened to 0,
Just
1,
something that acts like null without being null.
Yes.
Not true nor false.
I'm trying to remember the states from VLSI. I think every bit can be 1, 0, high impedance, shorted to VDD, shorted to ground.
So
Darrick,
the state that shorted your chip out and shut it down, what's that one called?
So Darrick,
Sounds like a quantum Boolean.
It used to be true and false, right? Then we got truthy and falsy.
Yes.
And now we have true, false, truthy, falsy, and wishy-washy.
No,
Yes.
maybe.
I like wishy-washy.
Yeah.
Question is it one value or two values? And nobody can make up their mind.
Right, that's what I said. It's a quantum Boolean.
Is it wishy? Is it washy?
All right, let's try something different here, or we'll be done early.
We can talk about profiling. We've talked about time. We've talked about compilers. So
I can do a short
we talked about
update.
AOT versus JIT. So the question I have is, what do you record and how much of it? And
For HotSpot?
yeah, well, I know I looked up HotSpot. I know HotSpot. You'd record like there's like the branches basically, and that's about it.
No.
Okay, maybe I'm wrong. Okay, tell me what you record.
So you know presence or absence of loaded classes, and at the if the interpreter has never executed a branch of code that includes a reference indirectly to some class, it won't ever link the class. So that tells you that you never took that branch without putting any counters on it. There's a counter on function entry, there's a counter on backwards branch. That's the interpreter, plus all the I never got here things. Then you get into sort of reasonable compiler counts. C1 will throw in counts for, like at Azul, I made it do Lars Ball, but I think at Sun, it was only ever doing more intelligent, less intelligent, just I took this branch left or right. Again, at Azul, I made C1 do tiered counters. So if you C1 inline, you got different counts. And then the according to which path. And then when C2 came, if he followed the same pattern of inlining as C1 did, which he typically did, he could use the sharpened counters along those paths. And then after that, there's some heroic bits that you usually get from failing. Like this thing's only ever been a 0. I've never seen it be a non-zero. I've widened this range check. I don't know, there are like 20 or 30 heroic bits that were effectively profiling, but you took the hard fault and got recompiled again with the bit set the other way. So there were a bunch of proposals for counting that never happened. The number of instances, we did look for the number of instances on a class. So a class with no instances was known to have none, and so you wouldn't be there. So you weren't necessarily declared abstract, but CHA would come along and say there were no instances, so effectively it's an abstract class. But we never did the one instance, and then here it is. And so when someone says load an instance of golden init thingy, we could say there's only one golden init thingy, so the instance is also a global static. That was in the plan, never happened. So okay, you're not far off. Backwards branches, function entry, and I never got here because the byte codes were never flipped to their initialized state. The byte codes, by the way, the Java byte codes, the VM has extra byte codes it uses to say, I've been on this path before and done initialization of the necessary class. So there's hidden secret byte codes. So if I walk a class and he says, load a field and load a field from this class over here, and you've never been down that path before, it'll be the generic Java bytecode as stated. If you've been down that class, he will check that the class exists, check that the field exists, check that the things are initialized, seal and and then he'll change the bytecode to one that says, and here's the offset, and everything else is hunky-dory. And that tells you that you've been down that class and done all those things, or not. And then C2 will just say, you've never been down this path, so I'm going to cut it off. So maybe that's it. So what other things are you thinking?
Hi, Cliff.
Yeah.
I'm not quite familiar with the HotSpot compiler, but I have a question is, I remember it's a method-based compiler. So does the interpreter only profile the method entrance? Or I heard that you said there is profiling as a backward branch. Is that inside the compiler or in the interpreter?
Interpreter. So these days it's tiered. The counting in the interpreter is expensive because the interpreter doesn't know the right offsets and can't get them from the bytecodes easily. So it slows the interpreter down dramatically to do a lot of counting. So the interpreter counts method entries and method backwards branches. When those trigger, you go to a first tier compiler. In the first tier compilation, it's much cheaper to count. So it's like 10 times cheaper than the interpreter or more. It's way the hell cheaper to count. So you throw counters in. Now you get a lot more profile data. And then a second tier takes advantage of that to do no counting, but higher performance code.
So would it make sense to ahead of time compile the first tier so that you at least have lots of cheap counters when your application first starts and you're getting vaguely GCC-like performance when your application first starts, and then you do something smarter the second time?
Yeah, so this gets into Falcon and Arthur's not here today. the cost to do a tier 0 JIT is cheaper than a miss to main memory. So having to load the code is a loser over generating it on the fly. So you're faster to just load the bytecodes and interpret than you are to load stage 0 JITted code. That's almost true for stage 1. It's really marginal. So I would claim that you're better off JITting stage 1 into your L2 cache and running it out of your L2 than you are to load it from memory or from disk. This is the funny game. It's only C2's last tier that you win to pull it from disk.
So if you were writing an interpreter today, would you start with the level 0 JIT and just skip the interpreter entirely?
Yeah, I go back and forth. I probably would. I would certainly arrange the interpreter to be a fucking hell of a lot easier to call to and from JITted code. Like the stack-based interpreter is not the answer. So a register-based, excuse me, a register-based interpreter is probably as convenient as a stage 0 JIT. I go back and forth. I'll get there when I get there. One of those two will happen. It's either a register-based interpreter or a stage 0 JIT for the first tier. I'm currently
The use case I think about is Clojure. When I write a very small Clojure program, you can essentially never have anything that runs in less than 300 milliseconds because it's going to spend the first quarter of a second building the entire standard library and compiling large parts of the entire standard library before it calls your first line of code.
That's because
it would be kind of nice if that happened ahead of time.
That's because you've cycled so many loops that you so much code involved. The deal is that JITted code is order of magnitude larger than the bytecodes. So your time to load, usually in these large applications, the startup time is all time to load. Nothing to do with execution at all time to load. Disk assets, pictures, images, class files and tables and setup and shit. And then the million bytecodes that run before main in a normal Java VM, not even Clojure. Normal Java VM, there's a million bytecodes that run before main. Loading those off disk, that's where the time goes. Okay.
Anyway, if you really want fast startup time, Graal will let you do that now. And there's a Clojure project called Babashka, which is like a sort of Clojure interpreter that runs on it's written in Clojure, and it has a startup time faster than Node.js. Like it's fast.
Is it still running on a JVM?
Yeah. Well, it's compiled though. It's native compiled by Graal. So it's precompiled. So it's not JITted. So that the trade-off is that you don't get the JIT. But it's if you really want startup time, which, if you're running like bash applications, it's what you want, then it works good.
Okay. This is these are things that are under a few seconds. Milliseconds, 300 milliseconds.
I'd say under a minute. Like you're not going to get a huge improvement. The best you can save is a minute.
Okay, because my usual experience is that things that have lots of code going on at startup, such that the normal C1, C2 tier JIT runs, 90% of the JITting's done in the first 3 seconds. And now you just have butt tons of code you're running at startup, and there's no saving the butt tons of code. So the fix for startup was to not run butt tons of code at startup.
Yeah, but if your whole programming
right,
language,
but if you're in Lisp and your world is written in your world,
then it's a solution. It works well. People use it. People in the Clojure community seem to use it.
So what I'm hearing is you start up a normal. The process would be you start a normal JVM. He runs a large Clojure program. The large Clojure program then reads a second Clojure program, does some interpolation of Clojure to Java bytecodes, and then spits out the bytecodes. And then the fast startup is
that Babashka project. I think it's just a straight interpreter. It's not even that fancy. It's like I don't think it's compiling to bytecode even. So it's just really for small programs. Like
you're running the Clojure under an interpreter. Like the normal Clojure technology that I understand, and maybe I'm wrong here, is that he compiles to Java bytecodes.
That's right. Yeah. So this is a separate project.
That's two tiers of
Clojure.
Okay.
And then its idea is to take the same language and make an interpreted version that's whole goal is to start up really fast.
Okay, now I understand.
Pre-compiled thing.
You have two tiers of compilers that are completely unrelated. There's machine code for Java bytecodes to machine codes. There's Clojure to Java bytecodes. You're skipping the Clojure to Java bytecode step by pre-compiling it to bytecodes. And now you run, oh no, not even that, by running the Clojure in a Clojure interpreter.
It's compiling the whole Java environment because Clojure is like a kind of library, and I don't know too much about the internal details of this. Actually, I've never looked that closely into it, but just sort of as a response to this, to Aaron's comment.
Right, but this is sort of in a different level. It's the JVM running Java bytecodes that it has in its class files in its face. I'm saying the startup time is typically dominated by disk to get those things loaded into memory, and then tier 2 compilation when it comes around to it, which is several seconds in, but the original 300 millisecond run is all loading disk. It has nothing to do with anyone's JITting code.
Yeah.
In that time, the interpreter will run 1 million bytecodes, and C1 will probably kick in on 100,000 of those bytecodes. But C1 on 100,000 bytecodes will come back at you in 10 or 100 milliseconds, 10 milliseconds, something stupidly fast, and you won't care. It'll be under your 300 millisecond lit. You'll still be waiting on the disk. What you're saying is, if I wanted to run Clojure, which has bazillions of bytecodes to run it as a Clojure, the way it's been set up to run, where I read the Clojure and I compile it using some sort of Java program that compiles Clojure source text to Java bytecodes, can instead go to a version that says, I've pre-cooked the Clojure program down to some bytecodes, and I have some sort of interpreted runtime that's still running Java bytecodes, but I'm skipping the compile step from Clojure to bytecodes.
Yeah, well, I've pre-cooked this Babashka interpreter, which is a thing that is basically like Clojure, and not just to bytecode, but all the way to machine code. Yeah, to machine bytecode, not to like
machine code or Java bytecode. If you're running it at JVM, you're unlikely to be going down to machine code.
But isn't that what Graal does? The Graal native thing?
No, I don't know what Graal native thing you're talking about. I've never heard of that one.
Yeah,
kind of.
Yeah, I'm pretty sure that's what it does. Like, there's a
wait, I want to hear
side project of Graal which compiles like C kind of.
Yeah, a lot of folks will take Java bytecodes and ahead of time compile them, but there's no HotSpot JVM involved.
No, they're actually two. There was a stage if it's kind of halfly precompiled, it still requires to load some classes and set up some things, and there is a stage that it's only ahead of time precompiled. That's the native image Darrick was talking about.
So it uses one of the Java native compilers.
Native image is kind of a separate project to Graal.
Yeah. Well, what do you do with a native image?
You precompile your bytecode for your jar program to a native executable.
Yeah, okay. And then that native image, when it runs, it includes, for instance, garbage collection and multi-threading rules and things like that. How far is it?
I believe it does. It seems like the only thing that I've heard of that it's lacking is hot reloading. So you can't
which garbage collector is it using? Is it using HotSpot and what are the HotSpot flags for garbage collection with precompiled native code? I'm curious because this is like a tough problem.
I don't know.
This is what broke all the Java compilers years ago.
Yeah.
Like people said, no, we'll beat HotSpot, and they never did. And the answer was they couldn't do all things.
The native image does not beat HotSpot. It's slower.
Okay.
It starts up faster.
Gotcha. And what's it do for garbage collection?
Well, I'm gonna have to Google it.
Okay, fine.
Yeah, the Graal native image, if I remember correct, they implement the G1 garbage collection, but it's not, they're using the new VM, not the HotSpot.
Okay. That was really the question.
Yeah, so I'm just looking at the build options in the documentation for native image, and it has a --GC, and you can select either G1 or epsilon or serial.
The epsilon is the no GC. You know, you're never free, and you never run a GC cycle. Your program exits before you run a GC cycle.
Yeah, but they have G1 in there too. That's the, I think,
which means they're using HotSpot and they're pulling code into HotSpot somehow. Because G1's, you know, that's a full runtime, unless they have a re-implementation of G1. They could have a re-implementation of G1. That's not a small project all by itself.
Well,
Yeah,
Graal's
I
been a
think
big project for a while, right?
Yeah.
I don't know.
It will probably link the code for the GC. It will pull the code for the GC somehow.
Well, I would claim that G1 is so wedded to the HotSpot base, you couldn't tease them apart.
That may
without
be
pulling in
well
all
the
hot.
case.
And maybe it's not. You know, maybe G1 had enough of a separation. You could do it as a standalone GC algorithm. But you have to call stacks. You have to have stack crawling. You have to stop threads. You have to do. It's like a million billion things that HotSpot does. Make it possible to have G1 run.
It seems like native image runs on something that's a different runtime system they call Substrate
VM.
Substrate VM. Okay, I've heard that. Fine.
Yeah.
Right.
And that has de-optimizer, garbage collector, thread scheduling, etc. That's what they say.
Okay.
Yeah.
It's a hotspot minus or something. It's not a hotspot at all.
Yeah, it's
I've heard substrate before.
Yeah. So I think it's I think it's just basically designed for people who have these short running programs. They want all they care about is startup time.
Yeah.
Yeah.
Mostly. Or it's for example the Scala native backend. It has its own implementation of the image
this is
GC.
supported by Graal. They could get G1 going. It's Oracle supporting Graal, so
Yeah,
maybe
it's all an outgrowth from the Graal project.
Gotcha.
Half baked.
Yes. Well, in here, I can tell Graal's been half baked for a long time.
Well, it's not a JDK team project. It's a Sun Labs project.
Right. Okay. Yeah. Interesting. Yeah. Okay. Fine. Da-da-da. I didn't know Substrate came out of Oracle. That was a different thing. Okay. Or Oracle Labs. Yeah, maybe it works. That was the surprise. You said G1. I'm like, that's wedded into the hotspot. No, it's wedded into Oracle. Fine.
But it's slower for the optimized, the C2 optimized code. It's slower for sure.
Then okay, right. Yeah, but that doesn't. Well, it doesn't make sense to me unless they just skipped out, because if you're ahead of time, fucking throw compile time out the window and you go to town.
But you lose some of the
optimization.
They have I remember they have a enterprise version. They use a profile guided optimization, which shortens the difference between C2 optimized code and the native
But they're
code.
still not caught up with C2 ahead of time, and
last time I checked it, they didn't match the speed of C2.
Yeah, and they've been trying. I mean, fine. There's a long history there because the Graal guys basically outgrew from guys who said we can beat Cliff because we hate him because he's a dick. That was just a right dick too much of the time, and so they were like, no, we can beat him, and they never could. And they tried hard, and they screamed at management, and they got management to half believe them. And so that was C1, and then later it became Graal when they went to Sun Labs because they gave up trying to beat me. But I got shit. I claim I was only ever honest and straightforward, but perhaps not as tactful as some other people might be.
But
A lot
it's
of the guys you're describing left to go to Adobe at one point, and the rest of them went to Google to work
Yes,
on
and then
V8.
and then Go came out of Robert Griesmer,
Hmm.
which was one of the primary guys who was like, I'm mad at Cliff because he's right too much of the time and he's a dick about it. And I'm not trying to be a dick. I was just trying to be honest. What the hell are you guys doing this? You'll never win. And they're like, screw you. Well, okay, they never won. Stop. I'm digging my own grave. Fine. Like I said, I wasn't very tactful, but I tried to be honest. No malice ever. No malice intent ever. But I was certainly forthright with my opinions.
The saying in skiing is "There's no friends on a powder day."
Ah,
That's been
I
a culture.
see. I'm not a ski fanatic, so I'm not there, but I get the gist of it, yeah. It's your favorite project and you're gonna save the world, and here's this Cliff guy telling you you're not going to. It's like, I didn't make any friends. Fine. All right. What else? Bitching about history past. We can be done. I was gonna do a short AA update. It's short because I got my week cut off. And landed what Darrick said. I've spent 2 months doing bugs. Yeah. So, I'm finding and sorting bugs and error reporting and bugs and field and inference issues. And I have 2 more bug cases in front of me for field inference that are being obnoxious that I need to sort out and decide that I'm on the wrong path. I need to give it up. I have gone so far. I don't want to, it's the gambler fallacy. I don't want to give it up yet. Or I have to cut back my full inference on field names as a way to do overloads. And then I got cut off by magical mystery eye implosions. My eye fell apart. I had to get tack welded back together.
Those
Your
glasses
eye?
look good. You look very scientific.
Yeah, so Doc says should be fine, except that in the next several weeks, whatever event caused my eye to try to separate can happen again. So if any of the following symptoms show up, this is get me to the hospital now. The risk is permanent vision loss. It's
Wait, is this from the punching yourself in the eye or something else?
Yeah, no, I don't know. That was a week, and then a week later, this thing happened. There was no eye trauma that I'm aware of. In the week in between those events, the only physical things I did was I took chainsaw and cleared down limbs off my property, which gave me, elbow tendonitis issues, but nothing, no eye injury happened in that process. It was
just a tip if you want to share it with your wife. If she doesn't want to leave bruises, she should put the orange in a sock to hit you.
Yes, exactly. We had that discussion because it was too funny after the fact where we're drunk and like, holy fuck, what the hell happened there? 10 o'clock, the internet was out because tree fell on the cable like normal, and I'm staring out across the dark sky and looking down the lights on Santa Cruz. It's all very pretty, and there was a funny light in the corner of my eye, and I looked, what was that in the house? I turned my head and looked, corner of my eye again. I looked around, what? It was optic circle ring flash. It would make a perfect ring. That was weird, but nothing hurt. And there were a lot of floaters, and that was strange. No internet. I went to bed. In the morning, I got on my phone, read up, and it says, get thee to the hospital now. So I called up Kaiser, and they said, get thee to the hospital. And I got there, and the doc says, come on in, and then we'll look in your eyeball. And it took him a little while. I mean, I was there for an hour before a doc looked, and it's like, oh, look at that. You've got a, tear in your retina. Well, that'll lead to retinal separation. You'll go blind. So we have to fix that now. There, hold still while I shine this incredibly intensely painful laser light in your eye to tack weld the tear down. Oh, that was too much for me. So they said, okay, go down to the pediatric pharmacy and pick up some Valium. Now, why does the pediatric pharmacy carry Valium? But they did. And they were the closest pharmacy at the, Kaiser Hospital. So I grabbed the Valium and I stewed on it for an hour. And then I went back and laid on the torture table, and she does literally 100 laser zaps on your eye, tack welds your eye back together. And, you know, it hurts like hell. And then she says, you know, go home. Oh, the other thing, she put a magnifying glass directly on my cornea. Like, we're not talking close. We're talking on the cornea, which abraded my cornea and hurt like hell as well. But she looked real good and said, yeah, I got it right. It's good. Go home. Call me if anything changes. Take your Tylenol. Take your wine. Just de-stress. Chill out. So the rest of the evening was a blur. I slept fairly well. I'm here. I'm alive. I have floaters, but no peripheral vision loss, no apparent anything other than I'm at risk for the next couple weeks of more happening. Don't know why.
You'll be
And I'll
fine.
try to not punch myself in the eye again.
Yeah. Yeah.
Crazier.
It's amazing that they can put that back together, though.
So they said was they can't fold the tear, the separation. They can't put it back, but the hole it leaves behind leaks fluid and will continue the separation, and you'll lose your vision. So you have a tiny tear. It was the optic, just a couple cones was making a bright streak for being torn. So they go around the hole in your eye, the tear, and they tack weld it down, and that keeps the tear from spreading anymore. And the laser just burns tiny spots that she has to do 100 little tiny zaps, but each tiny zap is with this, staring into the full noonday sun thing. It's like fucking painful as hell. And it actually physically hurt too, but there's this, just looking at the full sun and your eye is burning out. That's what it was like. Fine. Okay, so gruesome, there it is. What a note to end on, right? I'm alive.
If you have a different topic.
Sorry, go ahead.
If someone have a different topic, or
after that go around, we can be done. All right.
What's upcoming for you on AA? Like, what's the next?
Oh, well, I get my bugs out, and then I will probably push the REPL back to master. That all it does is type expressions. It doesn't run them. So I'm on master now. Much of the stuff's been cleaned out. Many interesting test cases work just fine. This last go round caused me to redo how primitives got handled, so that cuts a lot of things out, and mostly it's back together. I'm getting funny situations with I want to say fully cyclic types doing inference on, and that's just getting into like how a bidirectional type in Hindley-Milner style bidirectional type inference algorithm actually has to work in the end. So I had all the easy test cases where I have top down only or bottom up only inferencing working just fine, but the full cyclic ones have required certain more behaviors that I wasn't getting quite right, and then getting those sorted out has been a bitch. And I think I'm running down the tail end of the last of those. So when that's done, it'll be get a typing REPL back to master. I don't have arrays, so I'm going to leave them off for a little while, and then do some cleanup, and then I'll have to decide. I'm either going to do arrays as the last sort of major language change I want to put in, or I'm going to go do an interpreter on probably on the Sea of Nodes IR directly as a executable that people can screw with. You don't have any arrays, so that cuts down a lot of things you might want to try, but it would let people write little tiny bits of code and see that it works and it makes sense. If I were to do language changes have to happen, they want to happen now. Theory gets solid, but the syntax and maybe a little semantics might want to be changed around, and that would be, you got to play with it. You got to code in anger, or is it legal wasn't here? Go write a hash table and see that you screwed up, or it sucks as a hash table, or whatever. It's hard to write, hard to read, whatever. Now is the time, kind of thing. But get my last semantic bug out, and then it'll get to where you can look at least a little bit of code.
Yeah.
2 years of doing typing.
Yeah, I actually on mine went back the other day to porting. So there's a big code base that I need to basically support.
Yeah, right. Yeah, yeah. That's your
It's
whole
written in
thing.
a different language. It's written in C with like intrinsics and stuff, and it's not very pleasant to use. And so I've been working through porting, and so far there's a couple of things like, you know, it does some weird. I mean, it uses some weird C++ tricks and whatnot in the original code, which I'm having to work around a little bit, but so far so good. But it's been interesting exercise to like do a little bit of coding in anger and think, okay, what is the compiler going to do? And get a little bit scared, like, okay, this is a lot more code than my sample code programs.
Yeah, right, exactly. Yeah, the whole difference between coding and anger and just like, oh, here's a cool test case. Oh, it's the poster child for how this works and how that works. No, coding and anger is different game.
Yeah.
Yep. Somewhere along there, probably a little past like getting an interpreter up at all will be like language integration to IntelliJ or something, a language server. Something that you could inspect and debug and start to mess around. So JITting code's a long ways off. I'm looking forward to JITting code, but I've been doing language theory. And if somebody wants to help me sort on language theory, I'm happy to do that. So
how far do you need to get on the sort of theory side that you're doing before you can start on the other parts? Does it need to be complete? Like you've got this sort of cyclic type stuff, which probably you could write a lot of code without hitting, as long as you are careful not to hit it.
It's all about what are the semantics of things. So you're right. You should be right. I'm able to hit them because I'm trying to poke at corner cases. The getting them wrong probably means going back and redoing some amount of implementation of every other portion of things, because you have to change how the language is designed. Like the language right now basically has a internal execution engine, an operational semantics, small step operational semantics execution engine, which is also true for many of the type lambda calculi. There was a known, sort of SECD machine you go to. So I have that kind of a machine. That would change if I don't get the semantics right on this field inference issue. Because it changes everything after it changes, including the interpreters and JITting and the semantics, and that might also change how you end up writing. Certain code idioms aren't allowed anymore, and whatever things that look like they ought to. Like I know I can compile them fast, suddenly I can't. I'm forced to have a multi-dispatch semantics, right? Like I don't want to do multi-dispatch semantics because I find that they look difficult for me to interpret what the hell you're trying to do. Like your intentions when you write large programs with multi-dispatch, Julia, cough, cough, Julia. Like I find it difficult to tell what the programmer intended here. If I end up having to do multi-dispatch semantics, then I need to have, maybe I want to change what my language looks like. So I'm hoping that I'm not in the land of multi-dispatch semantics. And I'm doing that because of the way I do the inferencing on the overloads, in theory, always has a bottom case and stacks up. So you can always say, this one has to be X because I had no choice. I had to force it that way. Because this is X, this is Y, this is Z. And it's just like you do normal expressions in C or Java, your leaves all got fixed because you wrote, X plus 1. Well, 1's an int, so X has to be an int-like thing, or you have the widening rules, whatever. You build up expression knowledge from the low-level pieces. I want to make sure that that's not going to change. And here I have a test case in my face where I'm having unexpected trouble inferring what the type should be. And the error message I get is broken. So it hides the fact that it had trouble finding the thing. So I need to go fix error messages. So I spent last week fixing error messages. I have a little more of that to go. Then I have a test case that ought to give me an error message. And if I flip it the other way, it ought to work. And if I leave it as inferred, it ought to infer because it should say the other one is broken. Well, the one that's broken is not giving me a broken error, and fine. So once I get that sorted out, yeah, I think as sort of fast as I can, I want to get to a point where I can execute. So this is the last piece I want to do before I get to execute. Like I thought I had it. I ran out of bugs. I found one last week. I ran it down to my error messages weren't propagating through the right way. The type error types weren't propagating.
So once you get past that and start working on execution, do you have like a general idea of how long you want things to take, or is it kind of just open to whatever long it takes? Like, I'm just curious if you have it in mind, not so much like.
When you say how long it takes, you mean execution speed or time to produce?
Development time. Yeah, like.
No, I don't have a deadline, and I don't have a timer on me or anything, so I'm going to take what it takes. I suspect I can get an interpreter out in a couple months, maybe less, 1 month.
Yeah, I was just curious if like you kind of like I tend to do this, like I measure my sort of like have a general sense of how long I want to take to get through to some point, and it usually takes longer, but I sort of want to make sure that is like declining, or if it's not, then what's going on.
It's not. It's my head has been out of that zone for so long that I don't trust my estimates myself. So I'm padding them dramatically. And that's because I'm still wrapped up in type theory.
Yeah.
Once type theory has settled down, I think I have a steady path to execution. I think that will be straightforward because I know the execution part very well. So I'm still stuck on type theory things.
Yeah.
It certainly has major implications for the standard library design.
Oh yeah, right. Yes. The first thing that happens in the standard library is you poke all possible corner cases to their max. Like I said, I don't have arrays. I know what I want to do with them. I don't think they have any special typing things. They're just one more bit of infrastructure to support while I'm working the bugs out elsewhere. So I don't need to have them in to get the field inferring bugs out. So then I'll put arrays back in. I have one hack I want to do with arrays that's unexpected, and that's just make them as the infinite extension off of every struct and not have a separate array class. There's a lot of goodness and light I see down the road for having all things be class-like, and I can just have field names with functions. So if I have an array in my hand, and I say I have an array, and I say
array and tuple are both subclasses of struct in your head.
So array, yes. And you say subclass, they're actually going to be the same thing, really, not really subclassing at all. A tuple is simply a struct where the fields are named 0, 1, 2, 3, 4, 5, whatever, how many fields you have. That's the only thing a tuple is. The fields have this funny name. And then they print weird, and the syntax parses them shorter and all this. But they go to the type system, they're just a struct with fields 0, 1, 2, 3, 4. That simplifies the theory side a whole lot.
Right. And array is a struct plus the constraint that they must all be the same size and type.
Yeah, and there'll be some prefix of not uniform fields, and a postfix, which is the infinite extent of things that are looked up by number, not by name, and all have to be the same storage class and the same type and whatever. Yep.
But what if I want to have more than one infinite thing, like a multidimensional array?
The multidimensional would just be another case of it's all the same, except that the dimension count would go somewhere else. This is not necessarily, I haven't settled on Java arrays. I'll probably not do Java arrays. I'll probably do C or Fortran arrays, C arrays. So there'll be some set of dimensions, and then there'll be some contiguous pile of data that you have a well understood interface to do shift scale add math. And then we'll get into slices and things like that afterwards. Slice is a different thing. That's just a little tiny wrapper around the multidimensional array.
I mean, I think it's a big win if you can get your API to work such that most functions don't care whether you handed them an array or a slice.
Yeah, that, like I said, that's a different piece. One of the notions is the array has storage and a slice does not. And the slice in my head is a sub piece of a storage element. And so they're semantically, they have memory lifetime differences. I would claim the storage goes one lifetime and a slice has a different lifetime. Like the storage has to contain all slice lifetimes. The storage lifetime has to, all slices have to be subsets of the storage lifetime. So those are kind of separately conceptually.
Yeah, that's a question I've had before of like, what should you allow a GC to do? Because I may have some giant string and I've parsed out some tiny slice of that string.
Mm-hmm.
Should the GC have the right to say, oh, you're not using most of this string, I'm going to make a new string that's just got the tiny part that you have a slice over, and then I'm going to free the big string?
I'm of the opinion that the current technology for memory storage for pieces, for containing, is still up to the user and not up to the system. So unless I've produced a type or a structure for which the system claims like Clojure's permanent types or whatever, permanent containers, persistent containers. Unless I'm doing persistent container kind of things, the system will not do that directly. So you will have to say, I'm throwing away the outer container and all internal containers go away. Or I have an internal container and I want to free it up from the external container and move it to a different external container, compacting it on the way. That's a job that you're going to do right now. That's my current thinking on that one. Okay, when is it correct and timely and efficient and well to do that? So if I write a particular, I want to slice out a person's name from a giant JSON wob of all names, I get one answer. If I read a large program text in and I take every variable in the program and just leave it in the string of the program and just put a pointer to it, then I have hundreds and thousands of pointers into this giant string. Is it time to reify each of the slices and get rid of the giant string? It probably doesn't actually save anything to do so, but it might cost me a lot of effort. So that's a call that I think I'm not willing to have the runtime make by itself directly. That's not a language feature. That's, you have to decide. So the GC will not compact for you unless we come around a long time in the future and say that. In particular, GCs have another issue, which is they don't run deterministically or in a way that's easy to manage and control. So if you happen to know that you have a giant thing and you're done with it except for this little slice, the GC has no fucking clue that that's true until the next time the GC bothers to inspect the entire state of the heap. Right? So until a full GC cycle runs, you don't get the storage back. Same as finalizers don't return you file handles or graphics card buffers for graphics or anything like that. None of that comes back until GC does a full sweep. Well, that's not necessarily the time at which you want to do that recycling. So I claim this is putting those on GC in particular is a bad plan. Now, putting them on some sort of scope stack storage, it says as I unwind my storage and they come out, I'm now done with this giant ass string. Oh, I had some leftover bits that I want to hang on to. There's some user mode compaction thing that you might want to say, or there's something to be done there. I don't know what, but the normal thing in my head would be, you know, scoped reclamation for large resources I want to hand manage, and GC reclamation for large count of small resources I don't want to hand manage, and I don't need precision on when they come and go. And then, you know, Rust or not the Rust like things. Like I think I can, in my type system, I think I can do a Rust like counting fairly straightforwardly, or what Levo is talking about doing, basically linear lifetime counting in the type system directly. And that would lead to, you know, without a whole lot of annotations, or hopefully no annotations, lead to lifetime management, at least for scopes, stack lifetime things. Is that, you got any more questions along those fronts? No, you've got baby to deal with. Baby's eating the mic, and you can't unmute. Get it. All right. Anything else? Yeah.
I'm wondering. I remember last time you mentioned the GC map, and the conservative GC. I'm wondering how much effort in compiler perspective about introducing the GC map.
Oh, yeah, sure. So in theory, it's easy. In practice, it's an infinite pile of fiddly little bits. It's easy to get wrong. So the debugging cycle was much longer than, know the debugging cycle was long and plan for it and hit your engineering to find your bugs easier. The actual effort is sometime throughout the compiler, track what's a pointer and what's not. And anybody who's got a GC-like language, that's usually pretty obvious. When it comes time to code gen, if you're doing anything to do with derived pointers into arrays, is very common as to compile optimization on arrays. You have to track the derived pointer and what they're derived from. Then when it comes time to code commit, after you spit out the bits for the code, you spit out you have mapping points. So if you do mapping everywhere, that can get really expensive fast. So you have mapping points where you've decided you're going to allow a GC to happen at these points. You crawl the IR, and at that point you record in some data structure what's an OOP and what's not. Because you get a lot of these and they're fairly large, you end up trying to compact, and then bugs in your compaction and bugs in your register allocator and bugs in your optimizer, the tracking pointers and derived pointers, all lead to failure to get the OOP map correct. Then you have a few thousand to a few million OOP maps, of which any one is only ever touched if a GC cycle happens at that point. So bugs in here linger. That's why I'm saying it's hard to track the bugs here. Bugs here linger because you might mostly be correct, except for 20 case. And unless a GC cycle happens, and then the GC cycle doesn't really crash you if it fails to crawl a field, if that field dies soon thereafter, if the GC doesn't actually move it or reclaim that storage or whatever. So these bugs linger, so you have to plan on fixing that. From the GC side, he'll at some point do a stack crawl. That's already the magic trick the GC has to do. Crawling the stack means he's crawling the compiled frame. He has to go to the compiler. Usually you take a return address, a hash lookup, you get a structure describing metadata for the JITted code. Then you look at the offset from the return PC and the JITted code, and you come up with an OOP map for that location. And then there's some structure that says, here's my stack pointer. When I went into the GC cycle, I spewed all the registers out. Now they're laid out. So the GC says register A went to stack 15. The OOP map said register A was an OOP or not. So stack 15 is an OOP or whatever. He starts the marking games. There's a lot of interaction between the two to get the roots figured out. Once the roots are figured out, GC does whatever GC does with roots figured out. But getting the roots figured out is a bitch.
Okay.
And bugs linger there. We had a lot of technology done in HotSpot to help find those bugs.
Oh.
The actual effort, a couple days to crawl on the compiler side and spit out maps. The actual effort on the GC side, it's probably months to get your stack crawl right, or to conceptualize it. The actual stack crawl, it's not hard once you get all the right original bits. Getting original bits suck. Wrapping your head around it, you're breaking all the language models. You're not C, you're not Java, you're not nothing. You're a machine code only now. But once you get the stack crawl sorted, getting it to the map to the garbage collector or the compiler is sort of a tedious, straightforward, not rocket science, tons of little fiddly bits to get wrong kind of step.
But I see, by using conservative GC, there is no GC map, right? So the compiler may not be affected here. But I don't see too much, language that use conservative GC. Is there any reason that not choosing that?
Yeah, conservative GC doesn't compact, can't move pointers, so you don't get compaction. That leads to a very diffuse heap storage, which leads to a lot higher cache miss rate and it leads to a higher total live memory because you can't find spaces that are big enough to recycle conveniently. So cost of allocation goes up, cost of just running goes up because you don't compact the heap. A thing that no one plans for in theory but works out well in practice is that when you allocate a bunch of things and running code, they're all allocated in order, many of which are used for a little while and die early, die young. Some are live for a long time. The live ones are now spread apart by all the temporary things. If you compact, the live ones all get together and they're typically accessed in that order. You made them, and then you made a bunch of temporary work, and you made a new linked list node, a bunch of temporary work, and a new linked list node. When you compact, your linked list is all in a row. And now the hardware prefetcher just prefetches and does the right thing.
Yeah.
So there is a definitely performance gain to have a moving collector. It's faster. You can run in the background. You can do a lot of fun things with them. It's fine.
Yeah.
That's why it's a lot more engineering too. If you want something out the door fast, grab a conservative collector. If you have another way to understand that you have a short lifetime recycling thing, like if you use, JavaScript uses a conservative collector, but they collect every frame refresh, right? They have a separate heap for the frame. They don't have to do anything fancy at all. You might have a GC cycle during a frame, but you probably don't. At the end of the frame, whack. Right? That's easy. That's more like an arena allocation. Then you might have a GC on your tab. Well, your one tab is not typically going to generate gobs and gobs and get really huge. So they don't bother with a exact collector on the tab by tab basis, but each tab is independent. So they let the tabs, be their own little GC cycles. I mean, different people do different things, but there's a well understood, my life ends here. You're doing blockchain things, you have contract, the life ends at the end of the contract. Okay, maybe just do fixed storage for that. I have 100 contracts or 1,000 contracts. I'm running them all. They all have whatever. But at the end of verifying this entire block sequence, it's done. Whack it off. Now maybe I don't need a moving collector. You run a JIT web app server doing, web portal things that runs continuously. Now you may need a moving collector. Varies by your application. In your case, maybe you get away with a conservative and it's okay. And then there's a lot less engineering.
Yeah.
That's no fun.
Sorry?
That's no fun.
Yeah, I know. It's a lot more fun to write one though. It's definitely fun to write one. All right. And now noon, I'm going to declare victory. Cameron, I got your video downloaded to my box. I'll get it up at some point. Yesterday's all such projects obviously ended at an early stage. So we meet again next week.
Bye, guys.
Bye.
Bye.